Okay, October, November 2022, paper 4, variant 3. Question 1. An airplane accelerates along a horizontal runway before takeoff. The airplane accelerates for 35 seconds. The speed of the airplane when it takes off is 72 meters per second. Figure 1.1 shows how the speed of the airplane varies between times 0 and 35. Define acceleration. Okay, we know acceleration. What is acceleration? It is the rate of change of what? Of velocity. Rate of change of velocity, or you can say velocity per unit time or change of velocity per unit time. Calculate the average acceleration between 0 and 35. What is the average acceleration? So basically, you need to find the total acceleration or the average acceleration. So v minus u over t. That's all you need to do. V minus u over t. So the final velocity was 72, the initial velocity was 0, and the time was 35. So 72 minus 0 over 35, which is around 2.1 meters per second squared. That's the average acceleration, the total acceleration of the whole graph or equation. The combined mass of the airplane is 1.1 times 10 to the power of 5 kilograms. Calculate the average resultant force. Can I find the force on the airplane? Yes, I can find the force. Force equals mass times acceleration. What is the mass? 1.1 times 10 to the power of 5, and the acceleration is 2.1, which would give you 2 point, around 2.3 times 10 to the power of 5 newtons. 2.3 times 10 to the power of 5 newtons. Around 2.3. Okay, so this is the force applied on the plane. The force provided by the engines of the airplane is constant. Give one possible explanation for the change in acceleration of the plane between 0 and 35. Why? So the force is now constant. If the forward force is constant, why is the graph this way? Why is the acceleration decelerating? Not decelerating, I'm sorry. Why is the acceleration decreasing? Why is it a decreasing acceleration? Because of the air resistance. So as speed increases, the air resistance increases, and that's a fact that we must know. As okay, as the speed increases, the air resistance increases. Okay, on figure 1.2, sketch a graph to show how the acceleration of the aircraft varies between 0 and 35. This is an acceleration time graph, which is, I won't say rare, but not as much as the speed time graphs. Let's take a look at the graph. Initially, the aircraft was moving with a, let's say, constant acceleration. This part might be considered to be a constant acceleration. And then this part was kind of moving with a decreasing acceleration. And then you might say that this part was moving with a much smaller constant acceleration, right? So initially, a higher constant acceleration. Initially, the slope was much larger, and therefore a much greater constant acceleration. And then the acceleration was decreasing, and then in this part, it was moving with a much smaller constant acceleration. So initially, you can draw a constant acceleration, which would be a horizontal line, right? Whatever the value of the acceleration was, it was moving with a constant acceleration. And then decreasing acceleration, you can draw a line, a straight line downwards, right? A straight line downwards. And then the last part, it was moving with another constant acceleration, okay? Another constant acceleration, which would be another horizontal line this way. That's it. That's all you need to do. Okay, up to the 35 seconds. Question 2. We have a tennis ball. Tennis ball hits the racket at the speed of 52 meters per second. The average force is 350 newtons. The speed after leaving the racket is 26 meters per second in the opposite direction. The initial speed, the mass of the ball is 58 grams. Can I find the change in momentum? Yes, change in momentum is mv minus mu. mv minus mu. But since the ball is moving in the opposite direction, which is a really important keyword, it's moving in the opposite direction. Therefore, the velocity would have to have a negative sign. One of the velocities has to have a negative sign. So for example, if you want the 52 to be positive, okay, so the 26 has to be negative 26. It cannot remain positive. Why? Because it's moving in the opposite direction. That's the whole point of teaching you what a vector is. Okay, 52 and negative 26, so mv minus mu, but the mass has to be in kilograms. So you have to divide this by 1000, which is 0.058. You have to divide by 1000, 0.058. So mv minus mu, the mass is 0.058, 0.058 minus, let's say, 52, times 52, minus 0.058 times negative 26. It has to be negative. Oh, one of them has to be negative. 0.58, okay, which would give you a final answer of 4.5 kilograms dot meters per second. Not meters per second, or newtons dot second. State an equation which defines the impulse in terms of force and time. Impulse equals force times time. Impulse equals force times time. Calculate the time that the racket is in contact with the ball. Can I find the time? Yes, if you have the change in momentum, which is the impulse. So basically, force times time equals impulse, and therefore the time would be equal to the impulse over the force. The impulse is 4.5 and the force is 350, which would give you a very small number, 0.013 seconds impulse over force. Calculate the difference between the kinetic energy of the ball before and after the impact with the racket. Before and after, how can I find the difference in the kinetic energy? Half mv squared minus half mv squared. Or you can say half mv squared minus half mu squared. Again, the same thing. Half mv squared minus half mu squared. Would it differ if I use a positive sign or a negative sign in this question? No. Why? Because the velocity is squared anyway. The velocity is squared, so it wouldn't differ. It wouldn't matter that much, right? Okay. Half half times 0.058. You can just open a bracket and add 52 squared minus 26 squared, which would be a lot easier. Times 52 squared minus 26 squared, which is around 58.8 or 59 joules. 58.8 or 59 joules. 59 joules. Okay. Figure 3.1 shows the cross section of a barrage built across a tidal bay. Okay, part of a tidal power station. The gates are raised to be open when the tide comes in. The gates are lowered to close when it is a high tide. Figure 3.1 shows the water levels. Complete the sentences to describe the energy transfers which take place when the gates are opened. When the gates are opened. Let's read the words or use the words from this list. We have tidal bay, the kinetic energy, the gates, the gravitation potential energy, the sea, turbines, water. What energy of the what in the is transferred? Let's try to make up a useful sentence. Okay, so gravitational potential energy of the so the water is coming in. So of the water, gravitation potential energy of the, so let's try to water. If you're not sure if it's gravitation potential energy or if it's kinetic energy, anyway, of the water in the what? In the bay. In the bay. In the bay. Water in the bay is transferred to what type of energy in the rotating? So what type of energy in the rotating? It's the kinetic energy. In the rotating what? Rotating turbines, which is used to. So you have the turbines, which are used to rotate the generator. So basically, the gravitation potential energy. Okay, the gravitation potential energy in the water behind the bay is used to rotate the kinetic energy. Or rotate the turbines. State one advantage and one disadvantage of tidal power as an energy resource. It's not that common to even have questions talking about tidal energy. But anyway, what is one advantage? Definitely, one advantage would be that it is renewable. Yes, it is renewable. What is one disadvantage? Yes, it may harm the wildlife. It may harm the fish in the sea, for example, or the corals. If you have some corals, you need to destroy them. You don't have that many places like the geothermal power stations. So advantage, you have to say, or you must say renewable. A disadvantage, high initial cost could be a disadvantage. Yes, it could be a high initial cost. You can say that. High initial cost. Okay, good. State the main source of energy. What is the main source of energy for the tidal waves? The main source of energy would be, yes, the moon. It's not the sun. Tidal, moon. The only source which depends on the moon, actually. Yeah. Question four is cancelled. All of it is cancelled. You're in luck today. All of question four is cancelled. Now, question five. Three identical dishes A, B, C contain equal volume of water. A is outside and in sunlight, experiences no wind during the day. Dish B is outside in the sunlight and experiences a strong wind during the day. C is in a dark room. Water evaporates from each dish. I think it's quite obvious which dish. Okay, I think it's quite obvious which dish would have the greatest rate of evaporation. Explain in terms of particles why the three dishes have different volumes of water. In terms of particles, when we need to talk about the evaporation, you would say that the the dishes in the sun, okay, receive a lot more kinetic energy or a lot more heat energy or thermal energy. Therefore, a lot of molecules have high, okay, the highest energetic molecules. They receive the most energy. So most or a lot of these molecules would be on the surface and evaporate. And then the dish with the strong wind, dish with the strong wind would have a lot more molecules being removed from the surface. Removed from the surface. So let's talk about them. First of all, the dishes in the sunlight receive a lot more kinetic energy and thermal energy, and therefore the molecules gain a lot more kinetic energy, gain kinetic energy, and rise to the surface. You might say, and escape, thus increasing the rate of evaporation. Increasing the rate of evaporation. Okay, so these are the dishes in the sun. What about the dish which is in the sun and has a lot of wind? You'd say that the dish with the wind, okay, has a lot more molecules, hmm, a lot more molecules being removed, okay, being removed from the surface. A lot more molecules are being removed from the surface, and thus what happens? What happens to the rate of evaporation? The rate of evaporation increases. Rate of okay, rate of evaporation also increases. So dish. I think this is C. No, this is B. This is dish B. Okay, and this is dish A and B. Define specific latent heat. Cancelled. Okay. Thermometer. Okay. Temperature. I think this is latent heat again. What happens? No, we can't say what's happening in each of the sections A, B, C, and D. Yes, we can talk about the temperature. Initial temperature of the ice. Okay, so this was initially ice, -60. So can I talk about what's happening in A, B, C, and D? Yes, that's quite easy. In A, what's happening to the temperature of the ice? Okay, temperature of the ice is increasing. You can say the temperature of the solid is increasing as well. So the temperature of the solid ice increases. In B, what's happening? It reached 0 degrees Celsius, so it's the melting phase from solid to liquid. 0 degrees Celsius. This is the melting phase from solid to liquid. And then in C, what's happening? It's all liquid now. What's happening to the liquid? The temperature of the liquid, okay, temperature of the liquid water increases. So this is liquid water now. It is increasing. And then in D, what's happening in D? It's boiling. It has reached 100 degrees Celsius. Boiling phase from liquid to gas. You might say in B and D, you have a constant temperature. Okay, you have a constant temperature in melting and boiling. Constant temperature. Okay, good. Figure 6.1 shows wave crests and the direction of travel for a water wave approaching a barrier in a large tank. Okay. The wave is 1.6 centimeters. Wavelength is 1.6 centimeters. On figure 6.1, draw the direction of the wave of the reflected wave. Draw three successive reflected waves. Okay, that's easy. Reflection. This is now reflection. Don't need to refract. Reflection. First of all, you need to draw the normal line. So we have the normal line, and then we need to measure the angle of incidence. We need to measure this angle of incidence. I think this angle of incidence would be around 25 maybe, or 30 degrees. Anyway, you need to measure it using your protractor, and then you have to draw the reflected, or the direction of the reflected wave. Direction of the reflected wave would move somewhat in this direction. So this is the reflected wave. I guess it's at a much smaller angle. Anyway, you have to draw the reflected ray, direction of the reflected ray, and then you need three successive waves at equal distances. You have to measure the distances. He said 1.6 centimeters. Again, you have to make sure 1.6 centimeters. And on these, on the direction you have drawn, put 3 points which are 1.6 centimeters apart. So let's put 1 point here, and then at 1.6 centimeters, and then another 1.6 centimeters, and draw three waves which are perpendicular to the direction of this motion. Let me draw using another color. You have to draw the waves which are perpendicular to the motion at this point. You have to draw the waves, okay, which are perpendicular to the motion at this point. Okay, now you have the same waves, but they are approaching a gap in the barrier. So definitely this is not reflection. This is not reflection. This would be refraction. Okay, I'm sorry, diffraction. This is diffraction, and as it's passing through the gap, it's quite obvious that this is a narrow gap. Okay, this is a narrow gap, so we need to use our compasses. Okay, drawing the three circular waves using our compasses. Again, he said draw three successive waves, so open up the compass to the first. Okay, you have the pointy edge in the center of the gap, open it up to the first wave, and then this way, and then draw a semicircle on this side, and then open up the compass to the second and draw another semicircle. Again, you're using a compass, so it has to be very accurate. Okay. And then open up the compass to the third one and draw another, okay, the last arc, the last semicircle. You'd have the three of them this way. Okay, the third one might not be exactly touching the gap, which is the barrier, but again, it's okay. You need to just draw these three semicircles. Hmm. The frequency of the wave is 4 hertz. Calculate the speed of the wave. Okay, no problem with that. Speed equals wavelength times frequency. The wavelength is 1.6 centimeters, which we need to convert to meters. Again, SI units. 1.6 centimeters, which is 0.010016. Okay, 0.16 times 4 hertz. Okay, 0.16 times 4, which is 0.064 meters per second. 0.064 meters per second. Okay, that's easy. State what is meant by total internal reflection. What is total internal reflection? The angle of incidence angle of incidence in the more dense medium. I've talked about the more dense medium is greater than the critical angle. So all of the light is reflected back into the medium. Angle of incidence from the more dense medium is greater than the critical angle. Okay, it's greater than the critical angle. So all of the waves, or all of the rays, instead of waves, we can write down rays, which might be better. All of the rays are reflected back. Figure 7.1 shows a ray of light from a source in a tank containing a liquid. The ray strikes the surface at an angle x. The refractive index is 1.5. The refractive index is 1.5. Calculate the largest value of x for which total internal reflection can occur. The largest value for x for which total internal reflection can occur. If I have the refractive index, if I have the refractive index, what can I find using the refractive index? The only thing that I can find using the refractive index alone is the hmm, is the critical angle. So can I find the critical angle? Yes, I can find the critical angle. N equals 1 over sine C. Therefore, C equals sine inverse 1 over n, or basically sine inverse 1 over 1.5. Right? So this is the critical angle. The critical angle would be 42. Critical angle is now 42. So x is 42. Is that correct? Would that be right? No. Actually, the critical angle would be with the normal. Critical angle, this would be 42. Therefore, can I find x? Yes, I can find x because this is, it's perpendicular to the 90 degrees. Can I find x? Yes, 90 minus 42. 90 minus 42, so this would be 48 degrees. 48 degrees. I know x is around, the critical angle is around 41.8 maybe, but we can just round it up to 42. Can I find the speed of light inside the liquid? Yes, speed of light inside the liquid. I have the refractive index. So N equals VA over VM. Therefore, VM is equal to VA over N. What is VA? The speed of light in air, t times 10 to the power of 8 over n, which is 1.5. The speed of light in the liquid would be 2 times 10 to the power of 8 meters per second. That was easy. Figure 8.1 shows an apparatus used to charge a metal by induction. Okay, so induction is cancelled. Okay, induction is cancelled. You're not required to solve part A. Charging by induction has been removed from the syllabus. On figure 8.2, draw an arrow to show the direction flow of electrons and explain how you determine the direction. Flow of electrons is always in this direction. Okay, the flow of electrons is always in this direction. Explanation, we might say that electrons are negative and they flow, or they move from the negative terminal, or you might say that the current is in the opposite direction of the electron flow or electron motion or whatever. Okay, you can say that the currents, not currents, only current. Hmm. Moves in the opposite direction of electrons. Okay, now moving on. Figure 9.1, you have a circuit, you have a diode, you have a resistor, alternating current. The frequency is 50 hertz. Can I find the time to complete one cycle? Basically, I need to find the period. How can I find the period um, of this AC? Oh, period equals 1 over F. So period equals 1 over F, 1 over 50, which is 0.02 seconds. That's it. Period. 1 over frequency. The peak potential difference across the resistor is 340 volts. Sketch a graph to show how the potential difference across the resistor varies with time for 2 cycles. Label the potential difference axis and label the time axis with values of the time. That's really good. This is a really nice graph. So you have a diode, which means that the current will pass for only half a cycle. Will pass for only half a cycle. First of all, can I draw 2 cycles? Yes, I can draw 2 cycles. Will they be full cycles? No. They will only be half cycles. What do I mean by half cycles? So if I start off with a sine wave, okay, it will be zero for a while, and then I will draw another half sine wave. Okay, you have to draw them relatively almost with the same amplitude. Okay, almost with the same amplitude. The peak, which is what is the maximum voltage? The maximum voltage is 340 volts. What about the time? You started with 0 seconds. You started with 0 seconds. After half a cycle, huh, after half a cycle, the time would be 0. 0.01. After a full cycle, it would be 0.02. After 1.5 cycle, it would be 0.03. So this is the time. We need to just write down the time. Okay? Hmm. Okay. A cloud chamber can be used to detect alpha particles and beta particles. Alcohol in the cloud chamber exists as vapor and condenses on ions produced in the air. This forms visible tracks, so you can see the tracks of the alpha and beta particles. Figure 10.1 shows the tracks of the source of alpha and beta particles present in the cloud chamber. Some of the tracks are short and thick, other tracks are long and thinner. Okay. State and explain which tracks are alpha and which are beta. If you think about it, which one is the short one and which is the long one? Definitely the alpha particles are the short and thick one. Short and thick. Well, while the beta particles are the long and thin. Long and thin. The explanation. The explanation. If we talk about the alpha particles, what is the distance traveled by alpha particles in air? We know that the distance of alpha particles are very short. We know that, for example, the ionization of alpha is very high compared to the beta. We know that the penetration effect of the alpha is very low compared to the beta. Okay, you can write them down. Okay, let's write them down. So alpha particles. Let's talk about the penetration. Okay, weak penetration. and high ionization. High ionization and short distance traveled. While the beta, you have stronger ionization. Ionization. You have weaker, I'm sorry, stronger, not ionization, meant penetration. Stronger penetration. Weaker ionization. Okay, weaker ionization. And then a longer distance traveled. Hmm. Radioactive isotope of sodium is used to detect leaks from water pipes. A nucleus of this isotope of sodium contains 11 protons, 13 neutrons. This nucleus decays by emitting a beta particle to form magnesium. Describe what is meant by an isotope. That's easy. Isotopes are the elements with the same protons, same number of protons, and different number of neutrons. Okay, so elements with the same number of protons and different number of neutrons. Isotopes. Good. Write down the nuclide equation for the decay from sodium to magnesium. Okay, so sodium Na. What is the mass number? Mass number would be 24. So Na 2411 gives off magnesium Mg and beta. Mg and beta. We know that the beta is 0, -1, therefore the magnesium has to be 24, and the proton number or the atomic number of the magnesium will increase by 1. Why? Because -1 plus 12 would be 11. Okay, this isotope of sodium has a half-life of 15 hours. The isotope of magnesium is stable and does not undergo radioactivity or radioactive decay. Suggest why these properties of the isotope of sodium and the isotope of magnesium make this isotope of sodium suitable to detect leaks from water pipes. So we use them to find the leaks inside the water pipes. How can I use them to, or why are they suitable for these, for this application? Basically, because the half-life of 15 hours. Half-life of 15 hours isn't that long. Honestly, it isn't that long. Therefore, and to be honest, it's not that long and it's not that short. If you think about it this way, 15 hours. It's not too long and it's not too short. We have other elements that can have a half-life of, we're talking about seconds or maybe milliseconds. Okay, half-life, a very, very short half-life. But for this case, it is a long enough half-life. 15 hours is a long enough half-life, and therefore, okay, so you can say that it has a long enough half-life, which can help us detect the leaks. Okay, which is enough to detect the leaks, but won't be harmful to us humans. If the remaining sodium or the remaining magnesium stays inside the water, it wouldn't be harmful to the humans in a couple of hours or in a couple of days. You can say also the magnesium is now stable, which is not harmful. Okay? Hmm. Figure 11.1 shows a solenoid connected to a battery. On figure 11.1, draw the pattern of the magnetic field inside and around the solenoid. Indicate the direction of the magnetic field with an arrow. Okay, this is a nice question. Okay, it is a nice question because we need to find the magnetic field using the right hand rule grip. Right hand rule grip. How can I use the right hand rule grip? Let me assume, okay, let's assume that the current was moving in the opposite direction. Let's just assume. I'm just assuming for now that the current was moving in the opposite direction. So for example, if the current was moving in this direction, okay, again, I am assuming that the current was moving in this direction. So using the right hand rule grip, I'll move with the current. My fingers, okay, my four fingers will move with the current in a let's say clockwise manner, okay, or anti-clockwise manner. Anyway, the thumb will be pointing upwards. So if I'm moving with the current and then closing my hand, okay, so the thumb will be pointing upwards. If the thumb is pointing now upwards, this means that the North Pole would be at this point and the South Pole would be at this point. Again, this is if the current was moving in this direction. But since the current is moving in the opposite direction, then the North Pole would be at this point and the South Pole would be at this point. Can I draw the magnetic field lines if I have a magnet with the North Pole and the South Pole? Yes, it's always moving from the North Pole to the South Pole. So basically, you need to draw a magnetic field line this way and add an arrow. Okay, for example, magnetic field line this way. Then you have to put an arrow. What about in the middle? In the middle, you need to draw a straight line. Let me remove the north and south poles now. Okay, in the middle, you have to draw straight lines. Why? Because inside the solenoid, you have straight lines. The field is straight. This is the north pole and this is the south pole. So it's going out of the north pole and into the south pole. This is how you can draw the direction of the magnetic field inside the solenoid. Okay, electrical power is transmitted at a voltage of 400 kilovolts. A transformer reduces the voltage to 33 kilovolts for industrial usage. Calculate the number of turns on the secondary coil. Calculate the number of turns on the secondary coil. Can I find the number of turns on the secondary coil? Yes, I have the equation. Okay, you have the equation VP over NP equals VS over NS. What is VP يا شباب؟ 400 kilovolts. You can just leave it as kilovolts. NP, number of primary coils, is 11,000. VS is now 33. Can I find NS? Yes, cross multiply. This is an easy cross multiplication. 11,000 times 33 divided by 400, which is 907. I think in the marking scheme it would be written around 910, probably. Okay, so it's actually 907. If you write it down as 907.5 or 908, again, it would be acceptable. Okay, okay.